And yeah, the next speaker will be Emanuele. And he did a PhD in AI and did research on time series forecasting. Yes, so welcome, Emanuele. Yes, he will talk to us about async I/O and yes, how it all comes together. Please welcome him with a friendly applause.
Thank you very much. It's clear that we are in a Swiss conference because my talk starts 2 minutes early. You will never see that happening in Italy. So let's get started. 2 minutes more, that's great. In the previous years, the Python standard library has been quite stable and we all like it. I don't know if some of you has had the pleasure of developing in JavaScript, but that's quite another word. However, 2 packages in the Python standard library have undergone significant changes. The first one is typing, of course, and the second one, probably you guessed it, is async I/O. Async I/O is a relatively new addition to the Python ecosystem, but it has its root in some concept that is much older than async await. Today, we will try to understand why should we care about async I/O, how does it work under the hood, and how to use it in practice. That's quite a lot for 20 minutes, so let's get started. Why should we care about async I/O? Well, the point is, let's play a game. Let's try to bring computer scale time to human scale time. So let's say, for the sake of the argument, that a CPU cycle lasts 1 second. It doesn't. It's in the order of fractions of nanoseconds, but it doesn't matter. Let's say it lasts 1 second. Then, how long does it take to fetch some information to the L1 cache, the fastest memory outside the CPU itself? Well, it takes about 3 CPU cycles, that is 3 seconds. Quite a short time. How long does it take to go to the RAM, to the operating memory of the computer? Well, it's about 4 minutes. And here we start seeing that it's already 1 order of magnitude more. What about going to the network? What about completing an HTTP request response cycle? Well, in this time scale, it takes 7.6 years. It's about as long as it takes to get an answer from the Italian public administration. So it's an awful lot of time. Oh, I know that in Switzerland things work differently, but I'm Italian, so I have my reference system. And this is something we do not like. We do not like our very fast CPU to stand there idle, waiting for some external operations to finish. And async I/O is the solution to this problem. It's the solution to the problem of concurrency, and of course, it's not the only one. Let's try to frame an analogy to appreciate the difference between true parallelism and concurrency. Assume you go to a post office. To a post office, you have many clerks that are waiting for you to serve your request. You only go to one of them, and at the same time, other customers are served by other clerks. The clerk does everything. It listens to your requests, it performs some operation on his computer or her computer. They go and fetch the mail that you want to take out, and so on. So there is one resource that serves one task and does everything. You put many such resources in parallel, and you have achieved parallelism, true parallelism, for which you need multiple resources. On the other hand, what happens when you go to a McDonald's? Assume you have only one clerk there taking your orders, but the clerk does not do anything. They do not take your order and prepare your meal and take your drink and prepare your your meal. They only do one thing and then they pass to someone else. The clerk takes your order, it inputs it in some system or they write it down, and then an external resource, the kitchen, does all the rest. When your meal is ready, the clerk takes the meal and gives it to you. During the processing of the meal, the clerk can serve other customers. So you have one resource that serves multiple tasks, not because it's serving all of them in parallel, but because it gives away some of the task to some external resources. And it's not blocked by such external resources. This is what happens with asyncio. This is concurrency without parallelism. To get a little bit more formal, you have three main forms of concurrency: preemptive multitasking, cooperative multitasking, and multiprocessing. In Python, these are implemented by three different packages, all of them in the standard library: threading, asyncio, and multiprocessing. This talk will only cover asyncio. What's the difference? Preemptive multitasking means that you use threads. You use threads, and in Python, at least up until Python 3.12, there is another talk today, I think, about free threading in Python 3.13, but at least up until Python 3.12, the global interpreter lock was mandatory, and so only one thread could execute Python code at any specific time. So having multiple threads really meant that you had multiple objects managed by the operating system, preemptive multitasking, because there is preemption which can be done by the operating system. The operating system can decide whether to stop or restart a specific thread. And it all happens on a single core because of the global interpreter lock. About asyncio, we will talk in details during this session. And multiprocesses really means making multiple copies of the Python interpreter and running each interpreter possibly in parallel, but in separate processes, which is separate objects managed by the operating system with different memory address spaces. It's much more heavyweight. It's the only way that you can achieve real parallelism in Python. I mean, real Python, not using the C or Rust extensions, up until Python 3.13. But today, we will talk about how to achieve parallelism without multiple cores, how to achieve what is really concurrency. And to do that, we will do the most dangerous things in public talking, that is live coding. So, okay, first hurdle is gone. The screen is clearly visible. So let's start by trying and using asyncio. In order to use asyncio, you have to write an async main function. So already this function is defined as an asynchronous function that is a coroutine, and it has this weird keyword await inside of it. We will talk about this later. But now I want to focus your attention about this line 11 of the script. In order to use coroutines, you cannot just call them and pray for them to work. If you just call a coroutine, it does not get executed. What you need to do is to execute it in an object called the event loop, which we will be analyzing in a few seconds. In order to create an event loop and schedule some coroutines inside the event loop, asyncio has introduced in Python 3.7 this very nice asyncio.run function that lets you pass a coroutine, and Python and asyncio.run will do all the rest. So if we click run here, it works. It prints hello, then waits for 1 second, and then it prints word. Right? Fair enough. Was it useful? No. But it's how you get started. What happens when we use asyncio.run here? Well, let's go to the second example and let's see. Before Python 3.7, this was the way of running an asynchronous main function, an asynchronous main coroutine. And this is much more explicit. If you actually open asyncio.run, you will see that in the source code, there is this snippet here. A little bit more elaborate, better level of management, but the idea is just this one. What you do is you create an event loop. An event loop is an object where coroutine can be executed. The difference between the event loop and the Python main thread is that the event loop knows how to interpret the await keyword. The await keyword means, look, I'm gonna delegate some operation to external resources. Hey kitchen, please prepare the meal. And wake me up when the answer is ready. Very good. And then we can use this event loop with this run until complete method in order to execute the coroutine. When everything completes, either with an error or successfully, we close the event loop. Good. Now we have a rough idea about the context where this asynchronous code is executed. Let's see more in detail how it works. I'm kind of a fan of Game of Thrones, so I picked some images from the series. We want to send 3 crows, number from 1 to 3, and we want to see how much it takes to send them and get them back. This send crow can be a placeholder for anything, a database query, an HTTP request, and so on. It's important to note that I'm always talking about something that needs an external resources, mostly needs some external resources to fetch some data. That's because this paradigm, concurrency without parallelism, is useful when you have an I/O bounded program. It's completely useless when you have a CPU bounded program. So if you think that your code, if you measured your code and it's spending lots of time waiting for network requests or database queries, then asyncio is a good choice. If your code trains on your network or does some other heavy computation, it's completely useless. It's actually dangerous and detrimental to your performance. So we start by picking a performance counter. Then we call 3 times this send crow function, and then we measure the time that it takes. We run. This is a synchronous example. There is no async await here. So as expected, it takes 3 seconds because every time we call send crow, we sleep for 1 second, and then we call the other send crow. So send crow 1, 1 second, send crow 2, 1 second, send crow 3, 1 second, 3 seconds in total. Very good. Let's introduce some magic with asyncio. We create a coroutine here, send crow. We use asyncio.sleep and we await asyncio.sleep. Once again, what does it mean to have async await? Async is a keyword used to define coroutines. Coroutines are functions that can be paused. Await means, look, this function is going to call some external resource. Wait until that external resource is available, then restart the computation from here. Good. If this whole things reminds you about generators, well, it should, because coroutines are actually built upon generators. We will see some bytecode later on that demonstrate this claim. And then in the main coroutine, again, we await the coroutine send crow. So this should be called asynchronous. We should run it, and we expect it to last 1 second, except it doesn't. And it still takes 3. Why? Because there are actually 3 types of awaitable objects in Python. There are 3 objects on which you can call the keyword await. They are futures, which are not meant to be used in end-user code, but only in internal libraries, coroutines, and tasks. A coroutine is improperly a function defined with async, and a function inside which you can use await. A task is a coroutine that can be run concurrently. So if you don't transform a coroutine into a task, you cannot use concurrency. If you either don't do it yourself or let some asyncio function do it for you. So what should we do? Well, we can do multiple things. The easiest one is to use an asyncio function called gather. So you create all the coroutines and then you pass them all to asyncio.gather. Asyncio.gather means take all the coroutines I'm passing you, transform them into tasks, run them concurrently in no guaranteed order. And this is important. There is no guarantee about the order in which the coroutines are executed. And finally, give me all the results, right? If a coroutine gets an error, then the other ones run until completion anyway. Very good. In this case, something different should happen. We should see sending cloud 1, then sending cloud 2, then sending cloud 3. And after 1 second, cloud 1 returned, cloud 2 returned, cloud 3 returned. Because now the coroutines inside gather are transformed into tasks and they are run concurrently. So they are all started at the same time. Once you reach await, they are paused and then they are resumed again once the asyncio.sleep completes. Let's try this one. Yep, there we go. Cool. So on a lower level, what happened here? So what happened was this await asyncio.gather is basically planting a flag inside the event loop. The event loop is a loop, is a while true, basically. It's something that runs indefinitely and every time checks if there is some code ready to be executed. At the beginning, the event loop starts, and what it executes is the function, is the coroutine main. Why? Because it's the entry point we pass to asyncio.run. Right. So we execute line 13. Good. We go to line 14, and we get await, which means stop here, wait for all the coroutines after await to complete, and then resume. We only have asyncio.gather, which is a function of the asyncio package. And this function takes all these 3 coroutines, it transforms them into tasks, and schedules them in the event loop immediately. So send crawl 1 gets executed, print gets executed, await. So it means flag in the event loop, stop here, wait for the resource from asyncio.sleep to become available. Okay? So now we have 2 flags in the event loop, gather and asyncio.sleep from the first send crawl. Second send crawl, same thing. We execute print, we get await. Once again, stop and wait for this resource, so the sleep, to complete and for the data to become available. What can we execute now? The third send crawl. Very good. So let's print. This can be done immediately. Let's execute line 7, asyncio.sleep, stop here. Now we are 4 flags in the event loop. The event loop runs, nothing is ready to execute, the CPU becomes idle for 1 second. Right? 1 second, everything is stopped. Then the operating system signals to Python that the first asyncio.sleep has completed. So the event loop cycles once again and sees one coroutines that is one task actually that is ready to resume execution. It is the stand_crow1. So it executes line 8, it executes line 9. The result is stored inside asyncio.gather, but not all the results are available. So asyncio.gather is not ready to resume. But then, other cycle of the event loop, we have sendCrow2, and let's assume, for the sake of the argument, that both sendCrow2 and sendCrow3 complete at the same instant, exactly the same time. So now we can resume the execution either of sendCrow2 or sendCrow3. The event loop cycles, it finds sendCrow2 first, and it resumes execution from line 8. It prints Crow2 returned, returns I that gets stored inside asyncio.gather, and the same thing for sendCrow3. Now, gather can complete because all the results of the tasks are available, and so also this await can be resolved. We can run lines 15, 16, and 17, and that's it. So, very well. Python 3.11 has introduced another way of running tasks, that is using task group. With task group, you have an asynchronous context manager, this one, and inside the asynchronous context manager, you can create as many tasks as you want with create task. Create task accepts a call to a coroutine, and then you can have all your tasks saved into a variable. In the dunder exit method of the task group, that is the method that gets executed when the last line of the context manager is executed, the task group itself awaits all the tasks. So you don't have to do it yourself. There is an await keyword hidden here so that you can forget to run it. Right? Very well. So after line 17, all the tasks are awaited, and then you can access the results like in line 19. If we run it, we see once again that we have exactly 1 second of elapsed time. This is the suggested way of using asyncio since Python 3.11. Not using gather, but using the task group. Okay, now, if you want, you will see this. You will see a link to this repository in the slides, and you will be able to check out a more complex example when we use a semaphore and an asynchronous HTTP library like HTTPX to perform multiple requests in parallel. The requests are run in parallel, the code is not. That's the magic, because you start up to 3 requests concurrently and then wait for one of them to complete before running the code that sends the other one. Actually, let's try this out. And we see that the first 3 requests are sent immediately, and then when the first one completes, the 4th one is sent, and so on and so forth. A semaphore is an object in asyncio that limits the concurrency. So if you do not want to do a DDoS attack on a REST API, using a semaphore is kind of a smart way and also a kind way to your servers. Very well. So this script is basically a very complex way of computing the sum of the first 20 natural numbers, and it's 190. going back to the slides, we survived the live demo. The last thing, actually the second to last thing I want to show you is this diagram. This is basically how asyncio works under the hood. It's what I've tried to tell you with the code. So in the main thread, you run an event loop. In the event loop, you have a task queue that is the place where the flags with the awaits get stored. Every time you reach an await, the task gets sent to that queue. The event loop is a loop, so at every iteration, it monitors if there is one or more than one coroutine task actually ready to resume execution. It takes the first task, it executes it until it gets either completed, failed with an error, or gets an await. What happens where all the tasks are awaiting for something? Well, what happens is that the CPU gets idled and it sends a blocking call to the operating system. That blocking call gets resolved where data becomes available at a specific port. So every task is linked to an operating system port, and when data become available to that port, the operating system signals that there is that task ready to resume execution. So ultimately, the kitchen is the operating system. It's the operating system that manages the resume of tasks. Very good. Last topic that I want to mention. How are coroutines implemented in Python? Well, before Python 3.5, async await, all the syntax that I've shown you before did not exist. Still, coroutines were already a thing in Python because they could be created just using generators. Think about this. Conceptually, a coroutine is nothing more than a function that has an internal state, and that can be paused and resumed from an external command. Another key feature of coroutines is that they can be composed with each other. So a coroutine can await another coroutine. Generators can do all of this. Why? Because by design, they can pause. When you yield from a generator, basically you're pausing the execution of the generator. They can be resumed from the outside, either by calling next or by calling send. So you can send data to a generator. And they can be composed with yield from. So even before async await, Python had everything to create coroutines. Don't believe me? Check this out. So this is the bytecode generated by Python 3.4 with a generator-based coroutine, and the bytecode generated by Python 3.5 with an async await coroutine. Find the difference? There is very little because they are basically the same. That's just because async await is implemented at low level with generators. There are some resources here. If you want to go deeper inside this rabbit hole, I strongly suggest you to do it because it's super interesting. And I'm Emanuele Fabbiani, and I'm an AI engineer at Extreme. I love to go through Europe, delivering talks about Python and about machine learning. Actually, I'm more into machine learning than into software engineering itself. So if you have any kind of feedback about this session, feel free to get in touch with me, either in these 2 days or on LinkedIn.
So we have time for 1 or 2 questions. So are there any questions in the audience? I don't see any hands. I would have a question. So you said like multiprocessing is a completely different thing than async, which yeah, is true. But can you combine it? That you kind of like extract and heavy computation and then asynchronously wait for it to be finished in a sub-process or something like this?
Yes, usually it's really what you want to do when you have long-lasting computations, because now that you have understood the conceptual model, it's easy to realize that if you have a long-lasting computation within the event loop, you're basically screwed, because the long-lasting computation will take control. The async paradigm is not preemptive. So once the long-lasting computation has taken control of the event loop, it will not release it until it completes or it fails. So all the other tasks that get scheduled just have to wait to start that execution until the long-lasting computation is completed. So what you do in, for example, an asynchronous web, in asynchronous REST API, like the ones that you can develop with FastAPI, is have the endpoint asynchronous, but then detach a background task with FastAPI to manage the long-lasting computation in another process.
Right. Now there, question over there.
Yes, can you explain once more the difference between the first two code examples where you change from async run to using a event loop? What's the difference?
There is none, because what asyncio.run does under the hood is an improved version of my code in the second example. So if you open the code of asyncio.run, you will find those 5 lines with much better code for error management and stuff like this. So they're conceptually identical, just asyncio.run is written by proper software engineers.
And when do you recommend to use creating your own event loop versus taking the async run?
I think that nowadays you only have to create an event loop if you have very advanced applications where you want to create multiple of them. Because asyncio.run uses the default event loop provided by asyncio, of course, and that's usually what you want to do. If you want to instantiate for any reason multiple event loops, if you want to create your own implementation of an event loop, that you can do. I will never do it, but you can do it if you want, because it's pretty complex. Then you can do it with the primitives that I've shown in the second example. You can create multiple event loops and run them, if you want, in parallel with different processes.
Thank you very much.
Thank you.
The question over here.
So I have a question about the code base and organizing a code base. So a few years ago, I wrote everything without async. And then I started using Redis, asyncio for Postgres and everything. And then I realized that my classes, I couldn't use the functionality. So I rewrote all my classes to be async def and so on. And now it works well. But what's your recommendation about this? Because you've probably hit the problem where you have some functionality at the bottom, which needs async, and then higher up it isn't async anymore. So do you have everything as async or just parts of your code base? What's your strategy?
So it really depends on your application. So if your application is like a standard web application where most of the time is elapsed either in performing HTTP requests or database queries, then you basically have no other choice than writing everything async, because it will be the asynchronous web framework at the top, ASGI, to manage all the concurrency for you. And for that to work, you need to have the endpoint async and the calls to the database or to the HTTP endpoints async. So everything in the middle needs to be async, because only coroutines can understand await. So there is no way of getting around it. Otherwise, you can do what I mentioned before. So segregating the long-lasting computation into proper modules and using something like a FastAPI background job in order to run them separately from your main code base. But I know no way of getting around the fact that if you have a synchronous code base and you want to switch to async, you have to rewrite everything.
All right.
I'm sorry.
Are there further questions in the audience? over there, the front, and then in the middle. First in the front, I think.
Thank you very much for the insightful presentation. You said your field is actually machine learning, so I was curious to know if there are any instances where this has actually benefited you in applied machine learning.
Well, not before large language models came out, because, I mean, in traditional machine learning, the difficult thing was training the model. And training the model is a CPU-bound operation. So no place to use asyncio. And all the main machine learning libraries have concurrency implemented as real parallelism at the C level. So scikit-learn does it for you, PyTorch does it for you way better than you can do by hand. And once again, it's a matter of real parallelism and not concurrency using async parting. When AI became calling some APIs, then the situation became quite different, because, you know, if you want to use a large language model or to use a diffusion model via API, well, that's no different from any other web application. The time is spent waiting because the CPU are on OpenAI servers or DeepMind servers, and then you can use asyncio proficiently and effectively.
Thank you.
Yeah.
Okay, I think this is the last question then.
Thank you. I'm not sure, probably it's a bit off topic, but basically I'm currently facing the problem that, for example, if I do some API requests to a server to fetch the data, after a while it starts to throttle me. And probably, as I understand, it wouldn't help me to make several requests in parallel, as you showed. Is there any other trick I can do to get faster my data?
I didn't get what's the problem. Slow response?
So yeah, probably the server after a while throttles me and says, okay, sorry, you're not allowed to do that many requests as you want. So for example, only 10 requests per second or something like that.
There is some Python library to do this kind of stuff, but actually asynchronous requests are about sending as many requests in parallel as possible. So
yeah,
probably you would get this problem worse by using asyncio here. I mean, what can benefit you is if you can send like 10 requests per second, you can use https.async client, that is the one I used in the example, to send all the 10 requests concurrently and then wait for these 10 requests to be served. But then you need some external control to make sure that within a specified time interval, you're not sending more than 10. Because the semaphore does not give you the primitives to say maximum 3 within a second. You can say maximum 3 in parallel, but not within a second.
Okay, no, but then thank you.
Thank you.
All right, so thanks a lot for your talk. And
Perfect. Thank you.